All right, sections 15.5 and 6, parametric surfaces and surface integrals. So I am not going to have you create parameterizations of surfaces. I'm not going to have you sketch those surfaces, nothing like that. So what I'm going to do is I'm just going to give you just the very, very basic outline sketch information of section 15.5, just because some of it we are going to see in section 15.6 with the surface integrals, and I don't want you to be blindsided with something and be like, well, what in the world is that referring to? So let me just give you some basic information. First of all, the parametric surface. Okay, so if we have x, y, and z parameterized as functions of u and v, y is equal to y of uv, and z is equal to z of uv, then the parametric surface is given by r of uv equal to x of uv in the I direction plus y of uv in the j direction plus z of uv in the k direction. This is the parametric surface. Man, that's hard to say. That's the equation of the parametric surface. Okay, now u and v are kind of they're their own plane, right? We've got the uv plane that we're talking about, and it's this kind of conversion of variables, this change of variables to uv, and this is happening in an open region D, the domain D for u and v. Okay, all right. Next, the normal vector to a parametric surface. So the normal vector to a parametric surface. So given our parametric surface R of uv, our normal vector N is equal to R sub u of uv, u naught v naught, excuse me, u naught v naught, crossed with R sub v of u naught v naught. Okay, so that's equal to the determinant of I, j, k, partial x, partial u, partial y, partial u, partial z, partial u. Okay, and then RV is going to be partial x, partial v, partial y, partial v, and partial z, partial v. So if we need to find the normal vector to a surface, this is how we would do that. Put blocks around it. Go. Okay. And finally, and this is what we're going to be using quite a bit in the next section, is the area of a parametric surface. So the area of a parametric surface, okay, that's going to be the double integral over s ds, which is equal to the double integral over the region D of the magnitude of R sub u cross R sub v dA. Okay, so that's where R sub u is equal to, as we saw above, partial x, partial u, partial y, partial u, partial z, partial u, and R sub v is equal to the partial x, partial v, partial y, partial v, partial z, partial v, just what we saw above there. Okay. Oh, and D is the open region in the UV plane. So if we were going to set that up, we would find a way to define that region, just as we have been doing with double integrals this whole time. Okay, so now on to 15.6, surface area. I'm sorry, surface integrals. I just looked at the word surface area there. All right, so here we go. We are going to let S be a surface given by Z equal to G of xy, and we're going to let R be its projection onto the xy plane. Okay. If G sub x and G sub y are continuous on R, and if F is continuous on S, then the surface integral, oops, there we go. Then the surface integral of F over S is the double integral over S of f of x, y, z ds, and that is equal to the double integral over the region R of f of x, y, g of xy, so that's our z, right, times the square root of 1 plus g sub x of xy squared plus g sub y of xy squared dA. Okay, so we might think of that in this way, the double integral over R of f of x, y, z, square root of 1 plus z sub x squared plus z sub y squared dA. Okay, now there's a reason we have it kind of in this form, right? But just so that you can see it, it's really just this as well. So why don't we go ahead and do an example here. Let's evaluate this integral, double integral over S of y squared plus 2yz ds, where S is the portion of the plane 2x plus y plus 2z equal to 6 in the first octant. Okay, so if we were to sketch this plane, let me draw the first octant here. If we were to sketch this plane and we had x, y equal to 0, then z would be equal to 3. If we let y and z both be 0, x would be equal to 3. And if we let x and z both be 0, y would be equal to 6. All right, so we are looking at this little chunk of the plane here. Okay. So it's just this bit of plane right there. Okay, so then what is what is g of xy? Well, z is equal to g of xy. So we can solve the surface, the equation of the surface for z, and what we would then get is 6 minus, go back to the primary color, there we go, 6 minus y minus 2x divided by 2. So g of xy is going to be equal to 3 minus 1/2 y minus x. Okay, so for our formula for the integral, we need to know what is g sub x and what is g sub y. So g sub x is just -1, g sub y is -1/2, and we can go ahead and set up our integral. So this is going to be our integral across our surface. Oh, I'm sorry. You know what? I'm not sorry. Totally doing this. So we've got our integral over our surface of y squared plus 2yz ds. That's going to be equal to the double integral over the region R, which is the region in the xy plane, of f of x, y, z, and z is g of xy, times the square root of 1 plus z sub x squared plus z sub y squared, so that's just g sub x and g sub y here, dA. Missed a parentheses right there. Okay, so what in the world is f of x, y, g of xy? Well, that was given to us initially. We were asked to evaluate this thing. So our function f of x, y, z was equal to y squared plus 2yz. That came right out of our original integral that we were asked to evaluate. So then that's going to be f of xy, g of xy. So wherever there is a z, we're going to replace it with g of xy. So this is y squared plus 2y times 3 minus 1/2 y minus x. So then what we obtain is a function in only xy. So this is equal to y squared plus 6y minus y squared minus 2xy. So the y squares will cancel and we get 6y minus 2xy. Great. So that's going to replace f of xy, g of xy here. Okay, so let's go ahead and rewrite our integral. So our integral then is going to be the integral over r of 6y minus 2xy times the square root of 1 plus z sub x, or g sub x, was negative 1 squared, plus g sub y was negative 1/2, so that gets squared, dA. Okay, so there's our integral. Now all we have to do is define dA and r. Well, dA is dx dy, okay, or dy dx. 1 plus 1 plus 1/4 is going to be 2 plus 1/4, so that's 8/4 plus 1 would be 9/4 dA. Square root of 9/4 is 3/2. I'm going to go ahead and pull that out. So this is equal to the integral over r of, okay, so if I multiply, this is 3/2. So if I multiply 3/2 by 6y minus 2xy, what I end up with is 3y minus 3 times 3, 9y minus 3xy, okay, dA. All right, perfect. Now we have to figure out what is our region. Okay, well, what is our region? Well, the region R is referring to the region in the xy plane. So recall, R is the region in the xy plane. Okay, so if we go back to our original drawing that we had, it looked like this. We came out here to 6, 3, 1, 3 again. Sorry, that's x, z, y. It looked something like this. Okay, so the region in the xy plane is this little bit right here. That's our region. So let's see what that looks like. Let's take a look at our region here. So that's the trace of our plane in the xy plane. So it's hitting 6 on the y-axis and 3 on the x-axis, and coming through here just like that. So what is the equation of that line? Well, we can come up with it using any method from an algebra class. We were also given the function for for this surface, and we can find its trace in the xy plane just by setting z equal to 0. So if we set z equal to 0 there, what do we get? We get 2x plus y is equal to 6, or y is equal to negative 2x plus 6. So our region R here is bounded above by y equal to negative 2x plus 6, and below by x equal to 0. Y equal to 0, the x-axis, sorry guys, y equal to 0. So that's going to be our boundaries on our region. So our integral then becomes the integral from, the x value goes from 0 to 3. The y values are going from I did it again, from y equal to 0 to y equal to negative 2x plus 6. And then we're integrating 9y minus 3xy with respect to y and then respect to x, right? So remember, these are y values and these are x values, okay? All right, so at this point, this is a very straightforward integral. I hope it's a very straight integral. So back to main color, this is equal to main color. There we go. There we go. Okay, so this is equal to our integral from 0 to 3 of, so integrating with respect to y, this is going to be 9/2 y minus 3/2 xy squared. Forgot to square both of those. And we'll evaluate that from 0 to negative 2x plus 6, and then integrate with respect to x. Okay, so that's going to give us from the integral from 0 to 3 of, so I'm going to factor the y squared out. So that's going to be negative 2x plus 6 quantity squared times 9/2 minus 3/2 x dx. Simplifying, we get the integral from 0 to 3 of 4x squared minus 24x plus 36 times 9/2 minus 3/2 x. Let's distribute all, and we get the integral from 0 to 3 of, let's see, 4x squared times negative 3/2 x would give us negative 6x to the third. Okay, so there's a cubic term. Squared terms are going to be 4x squared times 9/2, so that would be 18x squared. And 24, can't read my own writing, 24x times 3 halves x, so that's going to become positive 12 times 3 is 36x squared. What did I just say? 36x squared. And then just linear terms in x, we've got 36 times negative 3 halves x, so that's going to be 18 times 3, which is going to be, what, 60 minus 54? So negative 54x, and then negative 24 times 9 halves, that'll be 12 times 9 is 108. So it'll be negative 108x. And then the only constant term is 36 times 9 halves, so 18 times 9. So would that be 171? Positive 171. So I'm going to double check that with my calculator. No, that's not correct. I subtracted 9 instead of 18. Let's fix that. Okay, mental math. Need a good functioning brain for that, don't you? All right, so that's 162. Ooh, and I dropped my dx. That's bad form. Let's make sure we have that there. Okay, so I think this is good. So then this is the integral from 0 to 3 of negative 6x cubed plus 18 and 36 is 54x squared. 54 and 108, that would be negative 162x plus 162 dx. Integrate with respect to x. We are going to get negative 6/4, so that's negative 3 halves x to the 4th, plus 54 divided by 3 is 18, so that's going to be 18x cubed, minus 162 divided by 2 is 81x plus 81, and that's evaluated from 0 to 3. So we plug in our 3 and our 0 to evaluate. Oh. Did you guys see what I did? I see what I did. Negative 162x, integrate that. I've got to add 1 to the exponent. 162, no idea why I divided that by 2. Gooey. 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 162x, that's just 162x. Got all excited doing my division here. Okay, there we go. That looks better. Now I've got my descending order terms like I should have. So I'm going to go ahead and plug the 3 and the 0 in. When I put in a 0, each term contains a factor of x. It all goes to 0. So just plugging in 3, we get negative 3 halves, jumping ahead of my own brain, negative 3 halves times 81 plus 18 times 27 minus 81 times 9 plus 162 times 3. All right, and putting that into the calculator right quick, I get 243 over 2. So this integral evaluates out to be 243 halves. Okay, now there's no reason why we can't switch the orientation of the surface that we're looking at and how we want to integrate it. So that's actually what we're going to see in the next example. We're going to orient this from a different direction. So this is our example. We're not going to actually evaluate this, and I just want to set it up. Set up a double integral to evaluate the following. So this is going to be the surface area, so the double integral over S of 6xy ds, where S is the portion of the plane x plus y plus z is equal to 1 in the first octant, in front of the YZ plane. So this in front of the YZ plane is what's telling us that we are going to look at this from a different perspective. We're interested in this thing's projection onto the YZ plane. I said that's incorrect. The region that we're integrating over is its projection onto the YZ plane. There it is. So here we are going to integrate, you know what, back the train up. Try to write down what I just said. So this is telling us that our region R is in the YZ plane. That's what that's telling us. And so that's the region that we're going to integrate across. Okay, what have we got? We have got that f of xyz, excuse me, that's equal to 6xy. Okay, we know that our region R is in the YZ plane, so our g function is going to be of y and z. That's actually our x value. That's going to be equal to, just solve the equation for x, 1 minus y minus z. Okay, so then f of g yz is going to be 6 times x is now 1 minus y minus z, that's our function g, times y, which is just y. Okay? All right, and then I'm going to need my partials for g. So I need partial of g with respect to y, that's -1, partial g with respect to z, also -1. Okay, so the last thing that we are going to need to set up our integral is our region. So if this is x, y, and z, x plus y plus z equal to 1 is going to hit at 1 on each axis. So the region in question, the region that we are looking for, is going to be this bit here in the YZ plane. Okay, so this is our region R. All right, so that's the YZ plane is where x is equal to 0, so we zero that out, and what we end up with is z is equal to 1 minus y for this boundary here. So z is equal to 1 minus y, and then of course the lower boundary is z equal to 0. And then y just runs from 0, another color, y just runs from 0 to 1. Okay, so those are going to be our boundaries for our region. And now we're ready just to set up the integral. So the integral, so y is going to be going from 0 to 1. Z is going to be going from 0 to 1 minus y. Okay, so then we're integrating first with respect to z, then with respect to y. Our function value we already have, that's 6 times 1 minus y minus z times y times the square root of 1 plus -1 squared, that's gy, plus -1 squared again, that's gz. Okay, that doesn't look anything like -1. Okay, let's try again, -1, there we go. So this is going to be our integral from 0 to 1, integral from 0 to 1 minus y of, so we've got 6, this evaluates to be the square root of 3, times 1 minus y minus z times y is equal to y minus y squared minus z times y, and then that's integrated with respect to z and then y. So just to simplify it, make it really clean and pretty, I'm going to pull the constants out. We've got y minus y squared minus zy dz dy. There we go. So that is set up and ready to be integrated. Okay, so just a quick recap. When we're looking for the surface integral, what we're going to do is we're going to identify function g. So surface integral steps, if you will, I guess, kind of the process. First, you want to find your function g. So g of xy or g of yz or g of xz, just depending on what orientation you're looking at. Determine your boundaries on R. Determine boundaries on the region R. You want to find f of x, y, g, or f of x, g, z, or f of g, y, z, whatever it is that you're working with, right? You're going to find that. Find the partials of g. Set up and integrate. That's it. So then plug into the formula and integrate. That's it. That's what you do for a surface integral. So that's all I'm really asking of you here. Surface integrals can clearly get much more complicated than that, as all of our integrals can whenever we are trying to do practice problems. But that's the big idea of kind of the process for these. Okay, so one more thing in this section we're going to talk about, and that is flux. The flux. So flux is a measure of, for example, with a fluid. Suppose we have a fluid crossing a surface, right? Then flux is a measure of the volume of that fluid that's crossing that surface. So that's what we're going to talk about now is flux. So first I'm going to give you the definition, and then I'm going to give you the integral for it. Okay, so we're going to let f of x, y, z be our vector field. Okay, that's going to be equal to m in the I direction, n in the j direction, p in the k direction. Okay, where m, n, and p have continuous first partials. on the surface S, oriented by a unit normal vector. There's that n from before, n, okay? So then the flux of the integral of f across S is given by the following. The double integral over S of f dotted with n, and yes, n is a vector, f dotted with n ds, okay? So there's the definition. Now let's see what that's actually equal to. Okay, so this is a theorem in our book. This is how to evaluate it. So if we've got S is an oriented surface, given by z equal to g of xy, okay, and r is its projection onto the xy plane. Then that integral we have up there, the flux, is equal to the double integral over the region R of f dotted with negative g sub x of xy in the I direction minus g sub y of xy in the j direction plus k dA. Okay? Now, this is what we would use if our surface is oriented upward, and we'll be told that in our oriented upward. We'll be given that information in our problem. Okay. If it's oriented downward, then the signs change, right? So if it's oriented downward, we change the signs. Yeah, I'll just rewrite it. Integral over S of f dotted with n ds is equal to the integral over R of f dotted with positive g sub x of xy in the I direction plus g sub y times g sub y of xy in the j direction minus k dA. That's if it's oriented down. Okay, and how you can tell the difference is just what's going on with k. The partials of g are going to be opposite sign, like they're going to be negative if k is positive, they're going to be positive if k is negative. K is negative if it's oriented down, right? We're going down, and it's positive if we're oriented up because it's going up. Right? So there you go. So there's the integrals, the formulas for the integral of flux. And we're going to do very much the same kind of things where we are finding our function g, and then we are just plugging them in here, finding that dot product, and going to town with it. Okay? All right, so I'm going to stop this one here in the interest of time. If you have any questions, as always, please let me know.